Okay. We should start now or wait 1 minute.
Much.
Okay, so welcome everyone to the proposed Network Machine Learning Research Group. Thanks very much for attending. Today we have, I would say, a very nice agenda where we will cover very specific use cases on how you can use machine learning for network operation and management. We also have an architecture that more or less is what, let's say, it's a reference architecture on how you can apply machine learning for networking. And then we will have some challenges associated to this very exciting topic. So we will start by the usual administrative aspects related to IETF. So Shen, please.
This is our already number 5 meeting. We had 3 meetings before with IETF meeting and 1 workshop, number 3 meeting with the EUCNC conference. We had many good discussions before and regarding so many use cases. Hopefully, if we formally charge the working group, become formal working group, then we'll keep studying on the use cases and try to understand what the requirements or impact will we bring to the network. Some of them may request new standardization work in IETF, I guess. For today, we have only 1.5 hours. We did apply for 2 hours, but given the difficulty the IETF security has, we only get 90 minutes. That's why we didn't open the call for agenda after we had the primary call for agenda. We had, so many quality presentations, and we don't have enough time to hold all of them. So that's why we have this agenda now. This is IETF IPR policy. Everybody should follow the disclosure rules. And before the meeting, we had the NMLRG mailing list. And also we have the web page maintained by under the wiki. The meeting is chaired by Albert Campos and myself, Xinjiang. We had every slides uploaded on the material page of IETF. So the remote participation could access and say, yeah, we did 1 note taker. Any volunteer? Me? Thanks. This is agenda we have today. We have the expectation of machine learning to network management from NTT. And we have the machine learning intelligence and networking challenge opportunity and realities from Diamond Major. We have the intelligence defined network by me. For architecture, we have the service classification in 5G networks by Rina, who's doing that remotely. Hopefully, because that's 5:30 for her. Yeah, we actually, for the primary core agenda, we also have Telefonica, Diego Lopez, and the French Telecom Orange, Stephen Senecio, but they cannot be here on site given the location. So, and that's too early for them from the European. That's why we don't have them in agenda. But hopefully, if we have next meeting in Chicago, we will have them to speak their practice. At the end, we will summary and propose some future activities. Any agenda, Bash? Okay, let's start with Kuhi.
So it's my pleasure to to introduce you to Dr. Shiomoto. I think that from Entity, I think that what we'll present here is a very specific use case on how to apply machine learning, and it follows very well all the whole chain, meaning that from an Infocom paper to a proof of concept. So Dr. Shiomoto, the floor is yours.
Oh, thank you very much. Introduction, and thank you. And first of all, I'd like to know how many people are mathematicians in this room? Oh, maybe. And I'm not a mathematician, but I use mathematics to solve the real issue. So I hope you enjoy my talk. And this is outline of my talk. And I introduce the issue of the network management today we have in Entity. And almost every carrier has similar problem, I think. And then I introduce the concept of the data-driven management. It's using machine learning techniques. How we use machine learning techniques, I will explain the reason why we take this approach. And then I introduce two practice, which Chair introduced. We presented a paper at Infocom 2014 and NOMS 2016. And this is a challenge in network management today. In nutshell, complexity and high expectation to the reliability and the quality is an issue we are now having. And as you know, if we click the URLs, many flows are forked, and it is very complicated traffic. And also the many traffics are encrypted, so it is very difficult to understand what is happening in the network. And also we have many boxes in the network, switches and routers from various vendors, and the middle box and NAT firewall and security and etc. So we have many boxes in the networks from the various vendors. So it is very hard to manage the network today. And also the customer has a very high expectation to our networks because every people are using the internet as a usual life. And if we got a lost quality, we lose trust from the customer. And another aspect is that the disaggregation. And we are looking at the future network as can be disaggregated from the various components in order to keep a sustainable growth of the industry. And disaggregation, so today we have a vertical integrated system like routers, switches, and middle box. Those are a vertical integrated system. So it is very hard to introduce a new feature for these systems. And also we have a risk of the end of life of the system if we lose discontinuity of some key components. So that this aggregation, I hope this aggregation will solve these issues. And SDN NFV is one step for the disaggregation. So we expect this trend solve the future, keep the sustainable growth of our industry. But disaggregation makes better or makes worse in terms of the complexity. We have many components in the network, so the complexity is getting worse in the network if we use disaggregation. And how to deal with these issues. And so far, we are using a mechanics-based approach to manage the network. Mechanics-based is that we understand the complete mechanics of each component, how it works, each component in the network. So build on this understanding, we manage the network so far. But it is very hard to do such task because complexity, increasing complexity. So we are looking at the data-driven approach. It's a holistic approach. We look at the system as a black box, and we look at the input and output, and we make a model from the input and output data. So this is a data-driven approach we call. And we have a variety of data source, and traffic load and performance and log data and travel tickets and SNS message, etc. We have many data sources, and we can make use of this. But this data is kind of numerical or text or a mixture of both. Okay, so I would like to introduce two use cases for the data-driven approach. So we have done so far. This is an Infocom paper, 2014, and this is a collaboration of my colleague. And actually, this is an academic paper, but we implemented part of this technology in as a tool, and our company are using in operation for the daily use for the maintaining a list of the syslog message. Okay, this is a background, and I almost explained why we use this. We take this approach, and but we have many syslog data generated from the network. And the problem is that the syslog is a vendor-specific format, and we have many boxes from the various vendors. And also the syslog is originally used for the debugging purpose, so it is not for use in operation. And we have a bunch of syslog message generated if we run a nationwide network. So the analyzing log is trouble, the challenge for us. And this is a research goal. We would like to mine the bunch of huge syslog data. Okay. And why we mine the syslog? We can find new alarm rules for the operator, and we can find a quick understanding of the root cause. And hopefully we can find silent failure. It is a very serious problem. And this is a key idea. And we have a bunch of huge syslog data. And we modeled it as a three-dimensional matrix called the tensor. And one axis is spatial, and another axis is temporal, and another is a syslog message type. So we model the whole syslog data like this. We understand what is happening in the network. So that we developed two technologies. One is a static template extraction technique. As I mentioned earlier, the syslog is a vendor-specific format. That we don't want to have a prior message, prior knowledge to understand the syslog message. So we use a machine learning technique to extract the template from the syslog data without prior knowledge. The second technique is LT, log tensor factorization technique. I explained the key idea in the previous slide, and we decompose the syslog message into the three we model the syslog message as a three-dimensional matrix, and we extract the relationship between the syslog template to the network event using the machine learning technique. This is the first approach. Idea is very simple, and we want to classify the word into the two parts. One is a parameter part, and another is a reserved word like this. So the idea is that if we find frequently the word in the location, certain location of the message, we understand that this is a reserved word. If we blue one is a parameter, if we this word frequently changed, if we and we understand this is a this. We understand it is a parameter. And so this is what I explained in the previous slide, and we score each word depending on the location of the message and the number of frequency, and we use a clustering technique to identify the reserved word and the parameter part. And this is a second idea. Yes.
Next one.
No,
Previous.
Oh, so go. And this is a second idea is log tensor factorization, and we define the two things. One is a template, which is a association between the syslog template, which is associated with a network event. Okay. And this is a second part is a network event. If we identify the template group, this data it represents this template. This log template happened both hosts like this. So this is a spatial information, and this is a temporal information. And this is a mathematics, but this is what I explained as a model of the syslog data. And spatial and the temporal and the message, log message. And we decomposed this three-dimensional matrix into three parts. And this is a template, log template part. And this is a spatial network events. And this represents a probability of what's happening in this part. Okay. Yes, this is what I explained in the previous slide. And this is a math, and this is kind of some kind of optimization, famous optimization. And this is evaluation. We collect the 5 million syslog messages, and we extract 2,000, 3,000 templates depending on the parameters. So we can reduce less than 1% log data. So we can identify the template for the syslog. And this is log tensor, second part of evaluation. And could you go next? Yeah. And this is a log tensor factorization and non-negative tensor factorization comparison. And I didn't explain the what is NTF, but this is a sort of the, we model the event as we didn't decompose the temporal and spatial in this test. So as you can see, if we decompose the temporal and spatial, we achieve a high accuracy. And this is a case study result. And This is we have two routers generated this kind of syslog message, and this is a probability, and this is also probability. So if we detect this kind of syslog message, we can associate with this is a link flap in this example. Okay, this is another example. This is a tunneling path disconnection example. So that this is again probability of the syslog message which we encounter this event. Okay, this is summary of my syslog analytics. And second, yes. And another one is trouble ticket analysis. This is also the joint work of my colleague and presented at the NOMS 2016. Could you go next? This is what we want to do, and we want to make use of the trouble ticket because the trouble tickets has a variable source for the knowledge to the network management. Okay, could you go to the next? And this is a trouble ticket example. And our goal is automatically extract the workflow from the bunch of trouble tickets for the similar network trouble. And we have two challenges. One is we need to find action from this trouble ticket. And the second one is branching action. We sometimes operator has a different skills to troubleshoot the network. So sometimes we have a branch for that. Even if we solve the same problem, operator takes different approach. So we need to identify the branching action. Okay. This is an approach overview. One is the labeling, and the second one is the alignment, and the third one is finding the branching action. Okay. The first one, labeling, is very simple. It's like a spam mail filter algorithm. So we use a naive-based algorithm for the spam mail filter. So we use a supervised learning algorithms to identify the action from the workflow, trouble tickets. And when we understand the action, we can align. Those trouble tickets is for the same network troubleshooting, and we need alignment for this sequence. But the problem is that the operator have different skills to troubleshooting. Some operator may skip some actions. And yes, here we use clustering algorithm. Yes. Could you go back? Yes, clustering algorithms. Could you go previous one? Previous one. Oh, okay. No. Oh, that's fine. That's fine. Yes. In order to solve the previous problem, we make a dynamic programming approach and some sort of similarity measure. We use the similarity measures. Okay. Could you? And finally, we need to find a branching action. So problem here is that we have some dummy branch action. We are puzzled with a dummy action because those actions are say some experienced operator just write write a replace module, but some young operator write this kind of sequence. But those are same. And this is another problem. This is a professional young man operators action, but sometimes experienced operator did not write this kind of action, even though they did it. So we need to understand those workflow. This is not a branching action. Okay, so the key observation is that we check the similarity between the action from the certain action. So if we find a similarity between these actions, this is not a branching action. But if we find those action sequence different, this is a branching action. Okay. And this is a mathematics, and I can skip here. And this is experiments. We have a number of trouble tickets for the different network event, network troubleshooting, and we tested the results in the next slide. And this is precision and recalls. And precision means that how accurately we identify the action, and recall is how we cover the target action. So as you can see, those are very high number, and we are very satisfied with this result. Okay. And actually, we tested the real work trouble ticket data, and we find extract the workflow like this. Okay. Maybe the next slide is and we also this technology introduced network operation in daily use in a production network, and we expect the machine learning to the network management, correlation and causal inference, and anomaly detection, and root cause analysis, and knowledge discovery. We expect for the network machine learning ability for the network management for this capability. Okay. Also, the prediction, detection, root cause analysis, and recovery is a phase of the network management. So, we argue that machine learning can be applied for every phase of the network operation, I believe. And this is the last slide. And network management is complicated, and it is very hard today. So we are looking at the data-driven approach instead of the mechanics-based approach. So the machine learning is a key technology, but I'm not so mathematician, so we need some sort of expert in this domain to make the network management better. Thank you for your attention.
Thank you, Dr. Shimoto. So is there any question, comments? I have some questions. So if you can go to slide number 24, please. Yeah, because I believe that at the end, this is the final result, meaning what you learn out of your data. What I don't understand very well is what are the probabilities? This is the correlation probabilities, meaning if event A happens, the probability of event B happening is this one?
This is one of the example, and actually, we use this technique to understand to maintain the list of the syslog message.
Mm-hmm.
Actually, the operator use a white list of the syslog, black list for the syslog message to pick up the network failure. And but operator need to maintain the such kind of white list, black list. It takes many human labors to maintain that kind of tasks. And because of the syslog messages hard to understand. But if we use these technologies, we can easily map the syslog to the network event. So that's why the operator can use. So
Okay.
this is just an example.
Yeah, I know. Thank you. So I have also more general questions. So I like very much your motivation that we must move from it's very hard to understand the specific mechanism, so we should move to a more data-driven approach where mechanisms are less important, but rather inputs and outputs. And I have like more general questions. The first one is, in this case, you are discovering knowledge out of your syslog data. I'm referring to the first use case. And in many cases, we have had many speakers, we have suggested that we could try to close the loop, meaning, in your case, you discover knowledge, and this knowledge is given to the network administrator to improve the network. Now, do you think that closing the loop, meaning that some sort of automatic mechanism is also used to take advantage of this knowledge to act upon the network, is something that we could foresee in the near future, far future?
Yes, it is. I'm interested in such kind of closed loop, some sort of artificial intelligence based network management. I'm very interested. But before we go this way, we have a lot of things to do. So we understand we have to share the practice like this among the community to how we can make use of the log mess. Many kind of data, and also we have trouble. We evaluate this technology because we cannot get data from the production network. It's very hard to get, but operators understand the value of our technologies. So the operator getting to feel comfortable to provide this data, such kind of data. So I think this is a good way, but we need to have many test data to test our algorithms. So
yeah, I agree with your point, and I think that there's also a trust issue, right? It's very hard to trust a system that will control your network. So first, you put a human in the loop that will take the recommendation and decide what to do. Then maybe in the future we close the loop. So another question is from your. So we have please.
Hi, this is Sudhin here. I have a question. Are you using any supervised learning or unsupervised learning? How you are training? Do you have a training data set? So what kind of intelligence? Because doing a machine learning, so you are predicting, you said you are predicting it, the future event. So what kind of algorithm you are using to predict the events? Like you are showing the syslog, it is going down. So you have to get the intelligence by running some algorithm or the data, the distributed data. So what kind of algorithm you are using it?
we present the two methods, and for the syslog part, we don't use a supervised learning. We unsupervised learning. So DB scan is a clustering. So we have a data, and we just clustering for the group of the data. So we don't use any training data for this purpose. But on the
Please go to the mic. Can you go to the mic, please?
Want to have no Vodafone. Does it mean that your decomposition of your big tensor at the very end is similar to a machine learning program which detects a pattern?
So it takes a time. You mean the CPU computational?
Yes.
Yes. It factorization takes a lot of CPU power. So this is kind of offline based for this technique. Is it the answer? Okay.
So how do you reach the conclusion? I mean, you have to have some algorithm to study the data, apply some analytics, I mean, mathematical formula to reach to a conclusion to say predicting, okay, this happens here. I mean, you have shown named Bayesian probability. So could you please explain how you are applying the Bayesian probability in this to calculating this?
Oh, this is a result of the optimization process factorization, matrix factorization. So we find a probability by matrix into the 3 pieces. So we can get the number for the probability. So it's something of mathematics.
Okay, the same can be achieved through formal methods, right? This was the method. The formal methods was developed in 1960. The same can be achieved. I just say input though. Thank you.
Also, I use for the second method, we use supervised learning, and we collect training data for the some network trouble, and it is very important to how many big data do we need to train the system. So this is another issue for the supervised learning.
This is Bing Liu. First of all, thank you. I think you really point out some essential requirement of how operators could see expectations for the machine learning technology. And I have two specific questions. The first one is regarding to the log analysis, because I always heard that processing the raw log data is always a big challenge. So from your experiment, do you find there's a very strong requirement that if multi-vendors can provide a consistent data format, then the machine learning could be much, much easier?
Yes, I think so. But syslog is originally for the debug purpose, so that each developer of the vendor understand, but other vendors do not understand. But if we standardize this kind of message, it's better. But I'm not optimistic.
Okay. I have a follow-up question. So I understand that there are, for the first use case, two main parts. The first one is taking syslog data and understanding it, which was the question. And then once you understand syslog data, you correlate the events and you obtain the knowledge. Which part was more challenging, the first one or the second one? So sanitizing, so one is understanding syslog data, and the second one is when you understand syslog data, you can correlate information. What was more challenging?
So the second part, we need the domain knowledge. So the network operator have to associate with what kind of event is related to the message. So I think it's a challenge, more challenging.
The second one,
yeah.
More than understanding the data.
Yeah.
Okay.
Okay. My second question, for your trouble ticket analytics, what about the training data amount? For example, you get the labeling of the trouble ticket. I didn't see the number in the slide.
Yes. I use supervised learning for trouble ticket analysis. We have some test trouble ticket, and we label each message is an action. So if we have a test data, and we can make a machine learning machine to classify the action. So new coming data for that. It's a kind of a.
So how many samples you need to train the supervisor classifier?
Okay, I forget the exact number, but I can send the information.
Thank you.
So someone here mentioned about the trouble ticket. So we've done some research in an enterprise setting, and we found that something like topic modeling helps a lot, which is a branch of unsupervised learning. The only challenge there is once you have done the topic modeling, the topics have to be assigned by the humans, but it actually works quite well, especially for text-based data. So I had another question, which was, how do you manage the false positives? Because if the rate of the false positives goes high, then it becomes a little bit of pain, which is where you said the network domain knowledge comes in. But how much of an overhead that was, weeding out the false positives after doing this process?
What do you mean by false positive in the trouble ticket?
Right. Like the classifier says, okay, these events are correlated and something could happen, but it may or may not happen, right?
Okay, so in the trouble ticket, we identify that this is an action. This line is an action for some action. So
That's even worse because if you assign an action based on probabilities, right? The thing there might be an anomaly, and then you assign an action. Hopefully, it doesn't have any effect on the network, but if it does, then it might change the network for the worse.
yes. So you mean that maybe we need to domain knowledge to
Right. Like for example, let me make it even more give a very specific example. So if you say A and B occur together, then maybe C should be the action. Now A and B happen mostly all the time in 99.9% of the time, but in 0.1% of the time A and B can occur, but C may not be the action in that case. And maybe it is maybe the action is maybe changing something in the network. During that 0.1% of the time, you will have trouble because you are not supposed to make that change, but it happened, right? So that's what I'm saying. Like when the false positive happens, typically that it feels that there has to be, depending on how the false positive rate is, typically there should be some kind of human intervention. So I just wanted, what was your experience in that? Have you experienced something related to that?
Maybe I think we can deal with branching probability from the workflow in the right. So
Yeah.
I show the branching sequence of the workflow. If we 99% go this way and but 1% go this way. So this is I think we can extract this kind of workflow. We can avoid this situation.
Yeah. For my understanding, up to now, most of machine learning mechanism is based on the analysis. It's actually some kind of ignores the the corner cases. But if we could build up a evaluation system to check whether the result from machine learning is doing something good or not, independently from the machine learning mechanisms. So we have the double check. Right. After that, only maybe until then we could apply the machine learning in a full closed control loop. Otherwise, up to now, there's more mechanism used for analysis rather than directly control. Right. And the reason I asked is, like, typically what happens is when you have a probability-based system, you probably want to have something like business rules as well. Right? Maybe so in that 0.1%, right, you maybe shut down one link, for example, but you might have a rule-based system saying that never do this. So you have a probabilistic system and you have maybe a statistics or a rule-based system, and human intervention, or maybe a human intervention without the statistical system. So that is where I've seen, like, just a probabilistic system never typically works in a real-world environment.
I fully agree. Yeah. So I have a very last question. So you mentioned on your motivation again that we need, and the conclusion that we need to bridge data science with network engineering, which is something very challenging, and this is what we're trying to do. And my question is, out of your experience, if you could compare the complexity of the machine learning techniques that you have been using to the complexity of machine learning when it's applied to other areas, such as computer vision. So do you think that we really need extremely sophisticated machine learning techniques as in computer vision, or those techniques are, let's say, a little bit easier? It's a complex question, but...
The algorithm used in this presentation, it is not so brand new machine learning, but we just extend the basic algorithm to tailor to the network management. So that maybe first we should do the machine learning, existing machine learning algorithm for network management. But if we need some, if necessary, we can extend the machine learning technique. So in that case, we need a expert from the mathematics.
Okay. Thank you.
Thank you.
So thank you very much, Dr. Shamoto. So let's thank the speaker. So our next presenter is Mr. David Mayer. He will talk about challenges and realities about this field. So you cannot change the slide, right? Or, no?
Let me see if I can.
No,
Is that all right?
You
You
need
guys
to
hear me?
Yeah.
Okay, this is going to be a completely different talk. I really enjoyed the last talk. It was really focused on the use case. What I'm going to talk a little bit about today is what is really going on from the technology point of view, and what are the challenges in this when applied to like when applied to networking. And I think Albert asked the question just now about do we need what kind of models do we need to actually solve this? I'll talk a little bit. I'll talk a little bit about that. I don't know what happened here. Can I do it?
No, you have to ask for
Can't change the page.
What's this?
voice command. This is a pointer. You can.
Oh, there's a pointer. Okay.
Yeah.
Go back.
Okay.
Okay. Well, this is going to be fun. Okay, so I put that up there because does anybody recognize what that is? The gradient descent, right? The gradient descent rule. Okay, so that's how we play it. Yeah. Okay, next. So here's my goals here. Just a little bit about what is practical, what are the challenges, and I put a footnote there that these challenges are not only technical, but they're socioeconomic, because a lot of this is about automation, and a lot of automation is resisted because, you know, what happens is people lose their professions and things like that. I'm not going to talk about that. That's a huge thing here. Retraining and how that's all going to affect society is just an entire topic of its own. And then a little bit about what are the opportunities. And again, like the previous speaker, I'm going to go easy on the math. Check out that URL. There's a bunch of stuff there if you're interested in that piece of it. Okay, so I heard this at the ONUG meeting. Wow, you know, machine learning is going to drive everything to be better. Next slide. Chris Wright, if you know Chris, great guy. He said this: it's going to automate your automation. This is part of the problem that we have with you know, people losing what their current professions are. Next. Yeah, but be careful, right? AI in itself, and there's a little URL down there. Hey, by the way, if you want the PowerPoint or anything like this, I hope that you guys will distribute it, but it's on my website too.
It is on the meeting materials.
Okay. So be careful with all of this. AI has failed spectacularly at least twice, going back to the 50s. So watch the hype. And I will tell you right now, the way to deal with this is first say, show me the math, then show me the code, show me your results, and then let me replicate them. If you can't do that, I don't know. I mean, I wouldn't trust it. Next. Okay, so, so here's a URL for some code if you want, and there's some URLs for some other information, but let's go to the next slide. Oh, this, okay, click. These were supposed to be hidden. Keep going, keep going, keep going. I left those in there so that if you wanted them, you could have them. Okay, keep going. Okay, so, you know, oh, wow, this really didn't work at all, did it? Okay, I made it on a Mac, and I guess this is on a PC, right?
Yeah.
Okay, so anyway, so in the, oh, wow. Even that.
What?
Okay, well, over to that side. This is working well. It was supposed to say use cases. So we got to find use cases that we want to apply machine learning to. Machine learning is not, we're not trying to do AGI here. We're trying to solve engineering problems with machine learning, okay? So usually we start off with use cases. We get a hypothesis about the use case. Like I just said, hey, maybe we can use autoencoders. I'll show you what this is in a second, to detect anomalies in data. And then we design some experiments. Then we execute those, and then we iterate. Machine learning is an empirical science, deeply empirical science. It takes a lot of compute, a lot of time to do this. So we, you know, in this cycle, what I did was I used workflow automation to make that happen fast, because you got to do this a lot in order to make this work. It's an empirical science. So next. So we've heard a lot about the successes of machine learning, all the hype. Where has it been? Hey, this is going to be hard to do because I built this with builds and they're all blown away. So I'll do my best. But so first off, where the successes have been are in this in these perceptual tasks, like Albert mentioned, vision, natural language processing, reinforcement learning for robotics, things like that. That's supposed to be the picture on the top. That's a convolutional neural network. That's state-of-the-art performance on vision. There's all kinds of statistical approaches. We just saw some of this. Some of it's based on Bayesian kind of approaches. Somebody talked about naive Bayes earlier. I'll just mention here, let's see what I can do with this. There's a problem here. Naive Bayes is really nice, but the problem here is that the evidence, the probability of the evidence, this is actually what's called the marginal likelihood. That's not tractable for any interesting problem. So you need things like approximate inference, variational inference, and things like that. So you got to know a little bit about that. Some anomaly detection has been successful. And what's really driven all of this, what's going on? Why is this all happening? Why are we even here? There's kind of 3 or 4 different things. One are these three fellows right here, Jeff Hinton, Jan LeCun, and Joshua. There were theoretical breakthroughs in 2006 that allowed us to train deep nets and overcame what was called a vanishing gradient problem. We can talk about what that is if people want to know. The second thing that happened was compute. There's more compute. When these guys first started trying to do this back in the 80s, compute was about literally 1 million times too slow. And then the advent of the hyperscales, Google, Facebook, Baidu, whatever, gave us data. And then now, recently, talent pipelines are filling up. So through universities and things like that. And so we've seen relatively little progress in the network space compared to this. Now, why is that? Well, it's because, can you back up one? It's really tough. It's because of these 2 things. That was part of the build right there. But because of, we can get the theoretical breakthroughs here in networking. This stuff's all available to us. We can get the compute. That's not magic. Well, a little bit, but it's not difficult to get. Getting the data and getting the talent are the problems. So let's talk about that for a second. I'm trying to catch up on the agenda. So these standardized, not standardized in IETF sense, but data sets that everybody can work out on have been just crucial to the success of machine learning. So that we've seen so far. So these are things like the MNIST digit database, ImageNet, 6 million images. Other things like the Allen Institute for Computer Science is now archiving data sets so people can use them, all kinds of things like that. But this allows for direct comparison of the performance of your learning algorithm and your inference algorithm on these different data sets. So direct comparisons. And the result of this is just the steady ratcheting down of error rates on these things. And now they're superhuman. So object and scene recognition, better than people. NLP voice recognition, this is Andrew Ning's stuff over here. This is in the 99 percentile. That's what makes things like Alexa usable or other things like that. Things like AlphaGo that can actually learn via reinforcement learning in different ways. And there's lots of these things. But the point I wanted to make here is that we just have nothing like this for networking, nothing. And I'll just say that most of the data sets are either toy, they're overly noisy, they're incomplete, they're unnormalized. You have to really, I think the previous speaker mentioned how much you have to work on these data sets before you can even start doing machine learning. Worse, many of them are proprietary. Service providers don't like to let you have their data, they're proprietary. Much of the data is of forms that aren't that easy to use, like maybe their time series as opposed to IID. IID means independent, identically distributed. If you can make that assumption, you can do all kinds of interesting stuff. And most of our data sources, syslogs, NetFlow, whatever it is, they really weren't built for machine learning, so we have to really work out on them. And it kind of suggests that maybe we're going to need some new techniques. That's not exactly clear, but maybe. And then the other thing is that there's no standard way to integrate these sources. So, these are all problems that we're facing right now. Next.
May I have a question here?
Yeah, go ahead.
Yeah.
Hey, by the way, if anybody wants to interrupt me at any time, just go ahead.
Yeah. By saying we don't have the the data provided by the network devices.
I can't hear what you said. I didn't understand what you said.
I mean, you just said we don't have the data source from the current network devices.
No, I didn't say that. I said the data that we have, like NetFlow, like syslog, like all that stuff was not designed for machine learning.
Exactly.
That's what I said.
Okay. fully understand. My question is, do you think, we need to do something for our network protocols or the network devices to be better suited for the machine learning?
Yeah, definitely. I mean, I think we could make a lot of progress if we could engineer that a little bit better, but there's problems with that too, right? Getting data out of these network devices is not a trivial matter. In fact, even without that, if you look at the sort of workflow that goes along with this, just ingesting large quantities of data itself is difficult, right? Yeah. So before you even get to any of it. Okay, so did I say that? Oh yeah, okay. Thanks for your question. Yeah, okay. So the previous speaker kind of touched on this. So machine learning is a form of applied mathematics, right? That's what it is. And it's multidisciplinary and it's empirical. So all of these things are playing together with these talent pipelines. Most of us network engineers, that's us, really don't have backgrounds that include the kind of mathematical training that you might need for this, most of us. And here's a kind of a little pie chart that shows you, but suffice it to say you need some chops. So it also requires additional skills, right? And so these skills are the ones I listed here. You got to be able to communicate. You got to be able to learn new things because the rate of change and advancement in machine learning is really staggering right now. It's just going so fast. And you also have to build software. You have to build systems that you can do this on, things like that. So the result of this is that there's kind of a serious skills gap in our community here. Open source frameworks, TensorFlow, I like TensorFlow, but there's Torch, there's many of these nowadays. Those are easing this up a little bit because you don't have to implement some of the more tricky algorithms yourself, but it still requires skill to, a really kind of intimate knowledge of the math to do this at scale. And most undergraduates and graduates right now are training on these perceptual tasks. So nobody's training people to do this for networking right now. So next. Now, so I used to train, thanks. What I mean by perceptual is, vision, natural language, things that you would do as a human, right? Robotics, can I do haptic interfaces and tell that you're out there and things like that? So I'm going to just talk briefly about anomaly detection. Go ahead.
Sorry, I have a question, Dan. On the previous slide, you said that the machine learning algorithms and libraries are making a lot of progress. So are you saying that that some of those algorithms and libraries are applicable in the networking space already?
Definitely.
Okay.
Definitely. Yeah. Let me just, Allison, 1 second. Okay. Let me just say one more thing about that is that what you'll notice is that all of the really high-powered machine learning things like Google, like Facebook, like Baidu, like whoever, Microsoft, they're all open sourcing their frameworks. And what this is telling you is that in a way, the value proposition is kind of going from algorithms because they're kind of, applying them is one thing, but they're all being open source now to the data sources, right? So the value proposition is kind of migrating from the algorithms to the data sources. So that's something we need to be aware of as well. Allison. Sure. Yeah. Say it again. I didn't quite fully understand what your question is. Anomaly detection for intrusions and things like that. Yeah, sure. That is. Yeah, I mean, generally okay, she's asking about threat intelligence and how that's derived via machine learning and basically, and on network data like flow data and things like that, right? And most, or syslogs, right? Most of that is about finding anomalies, computing a baseline, and then trying to either classify the event or just saying it's being generated by a different process. I'll talk about that in just a second, but that, yes, it's kind of the same thing. In a way, people need to remember, or people might want to remember, that learning is a very, very general thing. It's not really specific to networking. It's learning itself is very general, and we use the same algorithms to do all these things. So next. Trying to make it
sorry, let me break a little bit the agenda. I have a follow-up question to what Alison said. I think that something different is that we are trying to also apply these kind of techniques to control and management, which has not been done.
To what? To what?
A network control and management.
Yeah, I'll get there.
Okay.
Yeah.
Okay. Sorry. And let me follow up with what you were saying. So you bring pretty much two ideas. So we are missing, or we need a talent pipeline and data set. Okay.
Yeah.
Okay. So as for the data, we discussed this on the last meeting. But as for the talent, so we need to bridge, as Dr. Shimoto was saying, we need to bridge data science with network engineering. Now, my question is, do you think that we will take people from data science and we will teach them network engineering, or we will have network engineers and we will teach them data science?
Both.
Both.
It has to be. It has to be because, as I said earlier, it's a multidisciplinary kind of discipline, and you really cannot build use cases in a vacuum. So you need to know what these algorithms are doing. And especially if you want to do it at scale, you need to have intimate knowledge of what they're doing.
But let me then put an example. So typically, network engineers are pretty much all of them are taught Markov chains, which is a mathematical tool for network modeling. So why machine learning is that different from being taught Markov chains?
It's not. It's just that these kind of techniques haven't been taught to network engineers yet.
I know. But my point is, in the past, network engineers, so you didn't pick a mathematician and you teach them network engineering to do Markov chains. What we did was the opposite. We were teaching network engineers Markov chains. So to me, the answer is we will have network engineers which know about machine learning, not the other way around.
Yeah, I'm not arguing that.
Okay.
I mean, I agree with you.
Okay.
I agree with you.
Okay.
In fact, that's what I am.
Okay.
Right? I mean,
That's what we are pretty much.
Yeah. Okay, so let's just talk briefly about anomaly detection. So anomaly detection is the idea that you have some kind of what you're imagining. You know what? I kind of lost my flow on this because my slides got kind of broken here. So I'm going to have to kind of back up and say some things that I wanted to say earlier. But basically, when you see data from the network, what you're assuming is that there's some process somewhere that's generating this data. And what you really want to do, it's like a proxy for it, right? And what you really want to do is you want to understand that process, right? And so in the case of anomaly detection, what you're thinking is that you have some kind of maybe baseline or some idea of what it is. And that kind of tells you that this is the normal process of how this data is generated, the so-called data generating distribution. And in anomaly detection, what you're imagining is that, well, the first thing is that you find some data that doesn't conform to that baseline, right? And so you assume that it's being generated by some different process, like an attack, for example, right? And this, so these data don't conform to some kind of normal, some idea of normal, some baseline that you've built. And this actually has a lot of implications. And I want to say this earlier, and now I'm remembering. But basically, we really want to understand what assumptions we're making here. And in the case of anomaly detection, what we're assuming is, with this idea of baseline, is that there's some what's called stationary distribution. The distribution that's there is the normal distribution. And if we get data that doesn't conform to that, we assume it's generated by a different process. Now, that assumption of stationary distribution just doesn't hold, especially in the security setting, because it's generally an adversarial relationship. And if you're attacking me and I prevent that attack, you'll do something different. Hence, the distribution and the process that's being generating that data is changed. So this is a big problem. And I just showed you a kind of a picture here. Look at the one on the right. It's a little bit easier, just the one class classifier. These are the normal things. Somehow my anomaly detection algorithm decides that these two outliers aren't part of the same thing, and you declare an anomaly. And there's a lot of ways to do this. Somebody mentioned clustering. So millions of ways to do clustering: k-means, nearest neighbors, PCA, autoencoders. These are all methods to do dimension reduction, which is really what you want to do because you believe, or at least the algorithm believes, that somewhere inside this data is a lower dimensional form of this data, like a code, that actually includes all the information that you need. And if you could get it to go into a lower dimension, then you can compute much better, right? and you need fewer samples. So keep going. Oh, well, 1 second. This is what.
So sorry to interrupt. We're really out of agenda. If you can wrap up like in 2-3 minutes, we won't carry it away.
That's the end of my talk.
No, come on.
All right, go to the next slide. I don't know. Oh man, these are so broken. I'm sorry about this, folks. I wanted to show you, there's some other thing underneath there, and that was a build. I wanted to show you how you could do anomaly detection on a simple data set, which was MNIST. I'm showing you here. I used MNIST because it's so much easier to visualize the data that's like something that's in your experience. If it's network data, you don't know what it is. It's just, so here MNIST is these 28 by 28 handwritten digits. MNIST means modified NIST. So NIST data set. So they're labeled, but I'm not going to use those here. Go to the next one. I got 2 minutes. This is an autoencoder. It's a special kind of neural network. What you do is you take the input, you compress it, and then you blow it back out. So this thing in the middle where it says hidden, the 100 hidden units, that's sort of a code, right? And in fact, if you could reliably blow that back up, then you could actually just store those codes and then you'd have compressed. And a lot of, like Google does this, right? So the key characteristic is there's fewer hidden units than there are in the input or output. So what you're going to try to do here is the input is the MNIST thing. I flattened it. It's 28 by 28. 28 squared is 784. Compress it down to 100 and then blow it back up. And what you do is you look at the difference between the input and the output, and that's what's called reconstruction error. And then for anomaly detection, what you can do is you can just say if reconstruction error is above so much, you just declare an anomaly, right? So it's a kind of unsupervised learning. So keep going. What does it do? We don't have enough time for this. Next. Don't have enough time for this. Next. Keep going. I don't know how to do this now, but this was the code that did it. Here's the reconstruction error right here. This is the thing that was input. This is the thing that you got out of this little piece of code here. And then you just compute the out and you go, oh, this is a reconstruction error. And then if you want to know if this is an anomaly, you just have a hyperparameter, something you set, you don't know, hyperparameter you don't know. And you just get it, you just get a hyperparameter and say, hey, if it's bigger than this, it's an anomaly. Right? And so with this thing right here, well, sorry. What? I know, but yeah, okay. So, anybody else have anything? So that code's right there if you want to run it. There's an IPython or a Jupyter notebook there too if you like that better. So go to the next one. So this is what this thing did. I just printed out, if I use one example, the raw data is on the top and the reconstruction's on the bottom. Now in the one example, the reason the reconstruction looks random is because it is random. The weights were initialized to random, right? After 10, you're looking at it and going, it's, I don't know, it's getting better. After 100, it's getting a little better. And at 1,000, it's kind of looking good, right? And so what's happening here is that little autoencoder that we showed, it gets low reconstruction error on digits on 28 by 28 bitmaps that were from this data set and high reconstruction error on anything else. So you can declare an anomaly, right? If it's high reconstruction, it's pretty easy, right? This is a mean squared error, if you know that kind of stuff.
So maybe we can jump to the conclusions because we are really out of time. I'm really sorry.
It's all right. Okay. Keep going. 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 So maybe this is the right summary. There's lots of network data. It's not really standardized, labeled and unlabeled. But like I said, most of these things aren't designed for machine learning. There's lots of frameworks, so you don't have to, you can get a lot done without knowing things, but again, at scale, you still need to be able to know. Skills gap I was talking about still persists, and it still requires skills to build good networks, find good settings, prevent things like overfitting. If you know this kind of stuff, I don't have time to talk about it. But what I'm telling you is you're going to see this everywhere, so you need to start learning about it and learning what it means to you. So I don't know if that's all I have. Maybe I got out for you. Okay, let me just say one more thing.
Actually, can I ask you a question?
Yeah.
You had a slide, how is this applicable to us? How is this applicable to networking? I would be really curious to hear that.
How, which is,
This, because you said, how is this applicable? You had the slide that said, how is this applicable to networking? And you just said next.
well, that's because they asked me to do that.
Yeah, I know that, but I would be curious to hear that.
Well, so you can do the same thing. So what these turn out to be is, what I did was, it's a 28 by 28 digits. I think this is what you're asking. 28 by 28 bitmap, right? So what I did was I just flattened it. So now it's 768, or was it 784 bits long, right? Well, that's just a vector of what are called features. Now, if we have features from our network and we pick the right ones, that's another issue, feature engineering, then we can use exactly the same technology. Now, this didn't classify. Remember, this just is a binary. It's part of this thing or it's not part of this thing. You can also classify, but I didn't want to show that network because first off, I wouldn't have had time and it's a little bit more complicated. So yeah, you could use the same kind of thing. Okay, so go to the next one. I just want to say one thing about this. There's all these interesting things going on out here, but let me show you this one here on the bottom. This in this box right here. So there's 28 by 28 grayscale images, right? So how many? Suppose there's 8 bits of grayscale. Now, how many such images are there? Well, there's 256 to the 784, just a massive number of these images, right? The autoencoder, I didn't get to show you this, but 784 times 100 plus 100 times 784 is 1,000 or 156,800. So that's how many parameters there are. You might think about how you have to, what you have to do to compute that, but how much compute you need to do that. But if you look at 156,800 divided by this other number, that's 0. So how's this thing finding those? That's a beautiful mystery, And actually this paper here, Physics Perspective, tries to talk a little bit about the physics of this, right? But there's all kinds of beautiful mysteries in here that we can work on and that are applicable to us. So okay. I think I'm done.
Thank you very much.
Yeah.
So let's thank Dave. So let's move on. Next is Jen. He will present some sort of an architecture, a common architecture to apply machine learning to networks. We are not claiming that this is the architecture, but this is a good example for people to understand more or less which kind of things we could do. So Sheng?
Yeah. First of all, I have to apologize to David, also all of you, because we did apply for 2 hours session, but at the end we only get 90 minutes. So hopefully in the future we could have more time for discussing. This is the intelligence-defined network is one of the possible architecture we may be applied to apply the machine learning into the network. Next page, please. Yeah. At the very beginning for the network, we have the manually defined network, which has most of the stuff decided by the network administrators. They have to do it manually. For the last 5 to 7 years, we had the software-defined network, which in which we have the netconf YARN, and also for the loss-bound interface, we have the abstract description for the application requirements. Then translate that into the detailed forwarding table. That saves a lot of manpower for the network operators. It gets the semantic autonomic, but still the hard decision has to be made by the human beings. What we can see here is with the new mechanism, machine learning, what we would like to have the machines to learn the patterns of the network, like the traffic, like the application patterns. Then it may be possible to find a model to match the learned patterns and to make the decision for the network, how to run it, how to redirect the traffic to be better performance. That's the vision we want. Well, at the end, we hopefully to get the full autonomic with very minimal cost. Next page, please. This is a reference module based on the SDN or controllers already deployed. the SDN controller could do the quick control loop, and all those data from the network is collected from the measurement and also the status of devices, and that get together to a centralized point where we could, apply the machine learning algorithms to decide the policy, how we would like the network to be run, and how would like the network to be optimized. Then that's the policy, get distributed into the SDN controller, take the influence to the SDN controller, and to get every detail for the forwarding table. We also take in account for the customer order and the management interventions. That is also another input for the machine learning algorithm. And we hopefully will also have the API for the network requirements. Next page, please. What we did here is actually restructure the network towards a better machine learning based autonomic control and management. Just like what David said, for the current networks, the network and the network prototypes does not, generate enough data or the right data for the machine learning mechanisms. So probably we need to ask the question, if we want to apply the machine learning for the real-time management control for the network, what's the data we need, and how we get that those data from the network devices. Obviously, we don't have sufficient data for now. Then what's the next step? For us, hopefully, this we will say this is a network research issue rather than the machine learning research. The machine learning research already there. We have the those generic mechanisms, generic algorithms. The machine learning experts have maybe little or minimal interesting to learn the network. But as the network experts, we do have the motivation to learn at least some minimal knowledge of machine learning, so that we could use the new way to modeling the network to modeling the network data. And the rolling out of the machine learning managed network could be incrementally from the SDN-based network, and it also could be incrementally, case by case, depends on what the network and tasks we set up, and by doing all those, we'll see a lot of new requirements for the network towards the intelligence-defined network. Some of those may, lead new standards for the protocols, even new protocols. Definitely, that's out of the scope for our research group. But that could be some output from the proposed research group to, to give the recommendation what needs to be done in, in network devices and the network protocols. Next page, please. We could talk a lot, a days to talking about the availability of the network data. For the network, we have a lot of full of packages. For most of packages, we surely know what the size is, but for most of the packages, we don't know what the latency is, what the path it is. That depends on the measurement, but up to now, those measurement is most based on the, sampling, and that has some kind of representable, but still a lot of information lost. We don't have the exactly data for each package, and up to now we have we don't really know the network flow. For example, from the very first package, you never know it's going to be a very large and long-term flow or just 2 or 3 packages. As network devices, we can only know afterwards. But in different scenarios, like data center in Facebook or Google, they maybe face a different issue for their network because they generate this flows. So if they decided to generate a large long-term data flow, they could, use the flow-aware information to manage the traffics. Also use machine learning. And as we said, the current data is in different formats. Not only because the multiple vendor, also because the current protocol defined may not be, unifies the data. So that means for the machine learning, we have to do some probe proceedings before we can apply machine learning. That's actually a lot of work, and sometimes even more difficult than the machine learning research itself. And the network is complicated. We actually need to correlate from multiple tasks and multiple perspectives. Some of those tasks may, influence to each other. And the data selection is also the one of the main issue for applying the machine learning. Sometimes we have more data than we need, and we cannot allow to transfer every data. For example, if we have the data for each package, consider how many data we have and how could we gather them, over networks. That's too much overhead for the network by itself. And the quantity of data is also a big issue. Where is the enough quantity to be sufficient, and where those data will be stored? And if we want to apply the supervised learning, who could do the label for those data? Next page. On our side, if we has the machine learning mechanism, we get the result from the machine learning algorithms. We also need to design, what kind of the output we want to get from the machine learning algorithms, and whether they are applicable to the network. If we want to manage the network in a very large network, network-wide, then that means we cannot go very deep for every parameters on every devices. That's too much to ask. So probably what we could do is only on the policy level, but up to now we don't have the the unified description for policies, and the scalability. When the network become larger and larger, the machine learning mechanism may take much longer time to get to the result. And if we want to use machine learning to manage a large scale network, how long time we have to face for training? If we are talking about the controlling of the networks, that means almost everything should be done in real time. Yeah, we always think, the machine learning mechanism itself is something very, very difficult. We have a lot of mathematical knowledge to learn in order to apply the machine learning mechanism. we can't do that. We can't transfer every network experts into the machine learning experts. So that means we have to set up a way, an easy way for network experts to be able to apply their knowledge into the machine learning based intelligence. Next page, please. So this is how we separate the network issue and the machine learning issue. So what we want to achieve is by this reference model, then we can make it easier for the network experts to create the tasks. Only those blue box are, really the machine learning experts get to do. Actually, for the platform, we already have so many open source machine learning platform from the open source world. They has all those generic algorithms, and they manage the data, and they distribute the computing tasks. So what we would have is for the to have the interface to collect the data and select the data, to do the proceedings, to make the data be able to applied by machine learning. And we had the network policy task management function to do the training and to make the design, because sometimes training may be offline, take a long time, and we have to have the real-time design mechanisms which just apply the result from the machine learning. So then that could be in almost real time. And we have the intelligence network task description interface, so that the network experts could just describe the network tasks based on their network knowledge. Next page, please. This is an example how network experts could create the intelligence tasks very easily. Those network experts create just need very minimum machine learning knowledge. For the first example is traffic prediction. The network experts just need to describe the task, like to predict the traffic after 10 seconds or 30 seconds or 2 minutes, and where to. The task is only applied to select keynotes, which may have the traffic congestion highly possible. And they also could describe the relevant data, what data to be the input of the machine learning. Then we can probably get the result of prediction, like they describe the traffic changing in last hour, so that will take big impact to what may happen in next 10 seconds. And the traffic changing yesterday, the same time, and also the traffic changing last week, the same time. That's just describes the what in their knowledge is the most influence elements or data. Then the machine learning expert, the mathematical experts could take over from there. And any other human observed result could become the input. And for the traffic management, they just need to describe the.
So Shane, we really need to wrap up also.
Yeah, last page probably. Okay, I think next page. Okay. This is something we think as a research group we may have sometime need to give the recommendation for the network product like sometimes we need to say we need more data, we need new network measurement function, and how to select the network data and unify the data. Also, the policy description language and how to distribute those protocol, those policies to the SDN controllers and to which SDN controllers. Okay, I guess I'm done.
Okay, thanks, Chang. So we have a final announcement to make. So first of all, thanks all of you for attending. So in the last meeting, we discussed the importance of dataset, which is a topic that also we discussed a little bit with Dave Mayer. And another topic is that we discussed in this meeting is that we need to bridge data science with network engineering. So for this, so next slide, please. So one idea that we have is to write a project proposal for a SIGCOMM tutorial, which will be, this is the next SIGCOMM 2017, which is in UCLA, California. The deadline for the proposal is February. And what we are planning is to have, trying to bridge this gap, we would like to have industrial partners presenting use cases, very similar to what our first presenter did. So it's a very specific use case which is applied. And then also to invite open source platforms, as David suggested, on how to have some hands-on experience. So if any of the attendees fall into this category, please contact us. So we will prepare this project proposal. So, so that's it. Thank you very much for attending. Intense.
Yeah.
But it will work.
Yeah, I think so.
People will, they bring some important discussion.
Yeah, I think so. So. Oh, the blue sheet. Where is another one? Everybody, make sure you're trying to. Where is